Thank you, Vivian, for the great introduction, and thank you, Jim, for coming over here. As the topic is transportation, I hope it wasn't too congested on the way over during rush hour. So as Vivian mentioned, a while back, one of her students, came in and had this feeling that every time he was on the train, there we go. Every time he was on the train, it felt like this. And he couldn't get on the train, he couldn't find a spot, couldn't get in the door. So he found himself having to wait 2 or 3 trains before actually being able to go to work. And so he figured there must be something in the data that would be able to prove this. But obviously, as data scientists, we want to rely on more than a feeling. So we had to quantify this congestion that E was talking about in the Jersey City area. And we had to put numbers behind the notion that these trains were filling up to capacity before they were able to serve a potential customer, a potential rider. So how many people here have used the PATH train before? How many people use it on a daily basis? All right. So you guys already know the lay of the land, and Jim, of course. So the PATH train runs 4 main lines, from Newark to the World Trade Center, from Journal Square up to 33rd Street, the yellow line, from Hoboken down to the World Trade Center, and from Hoboken to the 33rd Street line. So there's obviously a lot going on here. But a lot of the action as far as pickups is happening in Newark and Jersey City. Now Jersey City here is, I think, currently the 2nd largest city in New Jersey, and actually fast rising, with articles like these from the Business Insider that's actually telling people move to Jersey City instead of Brooklyn because prices are better, and I think they list other reasons for why Jersey City is a very popular destination for people who want to work in New York but live elsewhere. And actually the mayor, Mayor Phillip, said that in 2016 the population of Jersey City is going to meet that of Newark. So we'll see if he's right. But if Jersey City is truly becoming the biggest city in New Jersey, congestion issues are going to become a pretty big issue in the future as well. Now, obviously the PATH Authority, the Port Authority and the PATH train system are doing all they can to meet these rising needs for their riders. Major innovations are coming down the pipe for the PATH train. If you search online, there's a public report on what the Port Authority is planning to do in the coming years as far as what they're renovating. In particular, they're expanding to Newark Airport. They're renovating the, I think, Harrison and Grove stations, and spending about $320 million updating the signaling system, which will allow trains to run closer together and increase the capacity for their ridership by 20% by the year 2017. So these are all great strides that are being taken to address this issue of congested ridership. And so it was not going to be in our domain to walk into the PATH Authority and say, well, look, we think you can do this better or that better. So we wanted to look at the data and give a way that we might visualize, help the PATH Authority, the Port Authority, visualize their data in order to support some of the decisions they wanted to make. We were given turnstile data in 15-minute blocks that say when people arrive to a station and when they leave from a station. And we were given the task of trying to determine where buildups occur. Now, obviously, there's a challenge here because trains come more frequently than every 15 minutes, at least during rush hour. So these were pretty coarse grains in the whole problem. There was no tracking of individuals, so there was no way to say somebody came on Journal Square and definitely left at the World Trade Center or at 33rd Street. So there was going to be some method of estimating where riders were going, estimating rider flow. And of course, this is all compounded by the fact that transfers were not able to be tracked because people are physically not leaving the system and coming back in at stations like Journal Square where they might transfer from the red line to the yellow line. So before we get into the whole approach on how we decided to visualize this, giving a little bit of a tease, this is looking at the Journal Square to 33rd Street line, showing on the x-axis here in minutes from midnight until 11:59 p.m. The number of passengers on each train as we calculated using our method. This red line is the recommended capacity by Kawasaki, the company who makes the train cars. And so we can see right around rush hour, I believe this is 8:30, 9 o'clock or so, the capacity is over that of the recommended recommended capacity for these trains. So this is a good sign for us. We could keep on going. Yes? We're going to get into that in just a few. So I just wanted to provide a little bit of a sort of a tease for what we're about to show. We're not going to wait until the very end to show you some of the data. But with that, I want to actually hand this over to Sylvie, who was able to help monitor these systems and model.
So the main problem we have here is like we have this 15-minute block of people entering and exiting, and we have no idea what's happening. So first, you can look at in a station when are people entering and when they are leaving. And this is the flux of people of passenger in the stations, like entry minus exit. And you can see that in a station in New Jersey, this is Journal Square. You have a huge entry, a number of entries in the morning, and people leaving the station in the afternoon. And if you look at Manhattan, you see the opposite pattern. People are leaving the station in Manhattan in the morning and coming in the afternoon, which is basically what you expect. People are living in Jersey, they are commuting to New York for work. But that doesn't tell you where these people are going in between. Like, are they going from Journal Square to 33rd Street? Are they going from Journal Square to somewhere else? So you need to actually model where these people are going. And to do so, we put some assumption on the data. Like, for example, we say nobody is going to go from 33rd Street to World Trade Center through the pass. There will probably take the MTA. Nobody is going to take the pass to go to 33rd Street from 23rd, 14th, 9th Street. Actually, they may, but we're assuming they are not. However, we keep Christopher Street because there is no real MTA station near Christopher Street, near the pass train, so we kept this possibility. We also think that people that are going to go from the yellow line to the red line are going to change at Journal Square and not at Grove Street. And that probably makes sense because like a lot of people are going to leave from the red line in Journal Square, so it would be easier to go into the train at that point. We also kept only the weekday data. We didn't take look at the weekend data because it was not really what we wanted to look at. And finally, we average all the data from all the weekdays together, so we may see less of a problem that there is actually on any given day. So first, we decided to look at when people are entering a station, for example, Newport at 9 in the morning, where are they going? So what we did is we look at every train coming between 9 and 9:30 at Newport, and see what exits there were on these lines, and find all the possible exits. And we also take into account the possibility of transfer. So if you go in Newport, you could take the yellow line toward Journal Square and change at Newark, and change at Journal Square to go to Newark. So if we look at this graphic, it actually shows you some people entering at Newport. They could take the yellow line towards Manhattan and go out at Christopher 9, 14, 23, or 37. They could also take the yellow line toward Jersey, go to Journal Square, change to the red line to Harrison or Newark, or go to Groves. But they could also take the green line to go to World Trade Center, or they could go finally to Hoboken. So at first we gave a probability of 1 to all of these possibilities, if a train is coming in the 30-minute window. And then we look at the exit. And so we have all these possible exits for each entry. We take every exit and we look at all the possible entry. And for all of these possible entry, we have a number of people in this station, and they may be different. And now we are going to put some probability. Like, for example, if 100 people are leaving Journal Square at like 6 p.m. at night, we may find that most of them are going to come from World Trade Center on 33rd Street. And to find that, we are going to look at how many people are entering in this station. However, we may see not a lot of people entering Exchange, like in the 15-minute block before they are leaving Journal Square. So not a lot of people are going to come from here. And that's basically how we put people in a train, depending on the probability where they're coming from. After doing that, however, we still have some orphan passengers where we found an entry but no exit, or we found an exit but no entry. And if you look at the repartition of this passenger, most entry without exit are in the morning, and most exit without entry are in the afternoon. And that makes you suspect there is something strange in the original data. And when you look at the flux of passenger in the whole system, so all the entry minus all the exits in the whole system, and if you look in the same 15-minute block, which is in orange, the green, people that enter at 9, for example, and leave the system at 9:15, which is the green line. And in blue, it's like people entering like at 9 and leaving at 9:30. Like that, we cover the whole system. And you see more entry in the morning than there is exit, and more exit in the afternoon than there is entry. So that's something in the data, and when we were in port authorities, we were like, yeah, they may just take the MTA, which is what we were suspecting. So we didn't want to get rid of this passenger because obviously they are entering the system somewhere and they are going somewhere. So to assign them to a train, we just use the probability we found earlier to assign them in the same proportion in different trains. So if this lost passenger here are entering in Junior Square, there is more chance they are going to exit in Manhattan somewhere than in Newark. So basically, with this input, the train schedule, the turnstile data, we decided the likely behavior of the rider, depending on the probability. And that gave us a goal for the visualization. We wanted to see the station level, like, because you have two problems. Can I go in the train? Or can I not go in the train and I'm stuck in the station? And how many trains do I have to wait? So you have trains that are too full, and you have people building up into the station. So we did a station level visualization and a system level, like, what is happening in the system? Where do we have problem? Is that in every station? Is that only in some station? So for the first visualization, it's like, this is represents the flux of passenger in one line, the yellow line from Junior Square to 33rd Street. In the first row, you're going to see the people in the station, entering the station, they are in the station, they are waiting for a train. In the light blue, it's going to be people taking the train at this given time. In the blue here, it's going to be people in the train, so you're going to see at rush hour that is building up. In the orange line here, it's people leaving the train at the given station, and in the red, it's going to be people left in the station after the train passed. Keep in mind, they may be waiting for another line. I mean, that's totally possible, but you're going to see that people build up during the day. And as you can see, more and more people are coming in Junior Square on Grove Station and are taking this train to go to Manhattan. And then it calmed down, which is exactly what you are expecting. And after, in the afternoon, you're going to see people building up too, but they are obviously coming from Manhattan, which is why you see them. So with this system, we can see the flux of passengers along each line. But you can't really, if I put all the lines in the same animation, it's going to be crazy. It's just like you get epilepsy or something. So it's not possible, which is why Tim built a system-wide visualization that is more, this will give you craziness.
So some of you may have seen me last week I presented. If not, my name is Tim. Thanks for coming. And so kind of to expand on Sylvie's algorithm, which will assign people to trains and also kind of track the people who are stuck in any one station, I also wanted to create kind of an intuitive way to view the entire path train system. And given, is this not working? There we go. And given that this is actually a train system, I wanted to see how that would play out when you look at it in terms of trains on the track. And so kind of what you see here is you see all of the train lines operating at approximately from 7, I think, until I did about until 11. And what you see is for each train line, there's a black kind of outline, and that's the capacity of that train. And you actually, or I should point out that the capacities of the trains are actually different across the different lines, and they're actually constrained by the length of the platform in some of those stations. And what you see actually here is the fill is actually how full that train is at that one point in time. And then kind of an extra level of detail, we have a unique ID assigned to each train. And so what you can do is you can track any one train over time and watch it get kind of full or not so full. And then you can track and see, well, where did this get full at what station? Or which train is causing is most backed up. So that kind of gives you a way to backtrack and decide, you know, or allows you to infer, well, there's probably people left at any one station because this train is clearly overfull. And actually, if you watch closely, let's play this again, maybe. Let's try this. There we go. And so if you watch closely, you'll actually see sometimes the fill on these trains will actually exceed the recommended capacity on any one train, indicating that those trains are actually, people are cramming on there. And so that's a really strong, there's one there. That's a really strong indication that there are definitely people left at that platform for all the platforms that that train kind of goes past. You know, nobody's able to get on after that train is over capacity. One thing that I did notice is if you look at this, this is really kind of hard to parse, right? There is a lot going on here, a lot of different trains, different lines. And so kind of to break this down, let's see if this works. There we go. And so, yes, the animation here. So let's skip slides here. There we go. Sorry. Fix this for me, please. There we go. And it stopped playing. You operate.
Yes, talk.
Okay, so anyway, so that last visualization was kind of overwhelming, right? Because there are a lot of train lines, a lot of things happening. And so if you want to kind of break this problem down even further, you want to separate out the lines, right? You want to see which lines are crowded, which lines are not so crowded, and you can kind of look down at a deeper level of detail. And so what I've done is I separate out each line and I give it its own little panel.
This is what the system looks like at night.
So give us just a second here. We'll see that actually the two lines that are in the two bottom panels are actually the most problematic lines, and they actually come from Newark into the World Trade Center and Journal Square, also into 33rd, I think, right? And so what you see is a number of overcrowded trains, and what you also see in the visualization is that those trains start as early as about 7 in the morning. And so, you know, I think we've kind of said before, there have been, or rather, train optimization has been kind of its own field of research since the steam engine was invented, you know. And so we didn't think that we could really tackle and solve this problem in kind of the 2-month turnaround time that we had. That would kind of be a ridiculously hard goal. And so really the power of kind of these visualizations is actually to allow people who actually do this full time and are train optimizers to play with the train schedule, adding more trains, subtracting more trains, just moving the schedule around. And then Sylvie's algorithm will automatically distribute those across the available trains. And then you have kind of a way to visualize those kind of in real time in a more intuitive fashion. And so that's kind of the power of these visualizations, and that was kind of the end goal of what we were trying to do. Because there's no way that we can learn an entire field of train optimization in 2 weeks. But what we can do is kind of provide a framework or a visual wireframe that would help people that do this full time to make their job a little bit easier. And so, I'm sorry, we're having a little bit of technical difficulties. I hope you kind of caught a snapshot. Maybe it's going to work now. This is actually kind of quite a lot of data, so it takes a long time to load from the web server. And so, you know, you can see problematic trains. Some of these trains actually leave Journal Square like that one already full, and that indicates that kind of probably stations down the line don't actually allow passengers on. And so basically this tool, we hope, will allow people whose full-time job it is to kind of optimize these trains to do their job a little bit easier. And with that, that's kind of what we've done, and we'd be happy to take any questions. Let me also point out, you'll see these flashing. That's because not all trains run at all times. And so if there's fewer than 4 trains, fewer than 4 panels will be shown. Questions? Yes?
So to my understanding, you count the people, not you, but the data, from turnstiles.
Mm-hmm.
I mean, people getting into the station through turnstiles, and then the same way leaving through turnstiles. What else was in the data?
That's all the
There were
data is.
stations and
Plus the schedule,
Yes.
the schedules, the train schedules.
The station,
right,
the station is also there,
So
and then we
from-
took a separate data set, which is the
okay,
train
you
schedule.
take this data and you combine it with your assumptions, and as a result, you derive your model, right?
Mhm.
Cool.
And so that was one thing that when we came to the patent.
So, which program did you use to create that model?
So this is actually all done in R, and so ggplot and ggmap actually make the maps, and then the animation package, basically you loop through every time slice, and then an animation package will wrap it all up together.
You had an earlier visualization that looked like a Sankey diagram. Was that what
Yeah.
you showed? Was that using a D3 to do that?
No, it's using a R package named Google Vis, so it's using the Google visualization tree behind, but I'm not doing it, coding it myself.
Very cool. Did you find any bottlenecks in those migration patterns? You know, in a particular station, you know, you started seeing that there were fewer people coming out of that than were coming in. Did you guys look at that, or?
Well, what we set out to find was the stations where people are unable to board, where people are left behind on the platform. And actually what you find is Journal Square, help me out with some of the other names. Grove Street,
Newport, and
Newport.
Exchange.
and Exchange. And so those end up just being pretty much the
The
closest
triangle.
stations to Manhattan. And so they're filling up in Jersey before they hit the closest stations to Manhattan within New Jersey.
Which is what people experience.
Which is kind of
but
what you expect.
It's nice to have it shown by numbers, and it also gives the tools to, if you want to try a new schedule, to see if it has a positive effect or not on the data.
Gotcha.
So, can you just clarify what orphans were? So the people who entered the station and then never left the station?
Basically, it's that. Yes, we couldn't find them an exit, but what happened is I think they can go into the MTA system without going through turnstile. Yeah?
I think they go through the turnstiles to go to the MTA, but there are handicapped exits. Most people follow the rules on the way in and use a turnstile on the way in. On the way out, there's a handicapped exit which will open. It is supposed to count users. So if a woman with a stroller walks through, it'll count 2 appropriately. But if 7 people walk through at the same time, and it's like to the sensor, it's just a max. And if you can't tell the space between them, then you can't really count them. So that's probably one of the anomalies.
Which package did you use for the animation?
Animation.
It's called animation. Yeah. Easy question. More like that.
I have a
Welcome back.
Maybe it's, you're from Port Authority, right? Like data from smart cards, right? A lot of people using smart cards or the MTA cards. Nobody's using cash apartments anymore. Do you collect that data, and is there anything interesting that actually potentially could be visualized or shared with the public?
Actually, I have very little exposure to this data, but the turnstile data,
It's similar, right?
yeah,
I think-
someone has to have a successful
Yeah.
scan to be able to open the turnstile.
Yeah.
So I don't actually know if the numbers you got came from the physical act of the turnstile turning or the snap of the
Yeah,
card.
ours were completely depersonalized. There was nothing. There was no registration. It was just a count per 15 minutes.
Yeah, so you couldn't tell like where the person entered and when they exited.
Right. That
Well,
was a
you
challenge.
put it anyway, right? Because
You don't have to swipe on the way out.
Unless you have the same ID on both the entrance and then when they come by.
Like Washington D.C. for example,
Yeah.
you have a zone system
Yeah,
where you swipe in and then you swipe out and it charges you based on where you get out.
yeah,
That would be a system where you might be able to see
yeah.
where people are going. In a crowded city like New York, it might be difficult to force people to insert a card on the way out.
Yeah.
So this kind of makes sense as far as here, but it would be nice to have similar data.
We're looking at other methods like iBeacons to sense Bluetooth in people's phone to track even people walking through the bus terminal and try to depersonalize it. We can't, if you sense a device on an iPhone or a mobile phone, you have their IMEI number or their SIM number, but we are looking to do that. So if we have 1,000 people walking into the bus terminal at a certain time, and we also have sensors at the exits, we know when the person walked in the front door, essentially when they arrive at the gate, because they become available to the iBeacon, and then we know within a certain amount of time when they're left.
And those are things we also kind of assume is that as soon as you come in the gate, you're taking the next train you can get. Sometimes, you make a phone call or you're not, you're lollygagging maybe.
So will your ID can work even if the Bluetooth set is turned off on the phone?
Then that's not a valid person to track. We're not trying to track individuals, we're just trying to get volume numbers. So, and even if we're not necessarily counting people, we're determining how long it takes for them to make their way through the station. So if we know, for example, similarly, if a bus with a capacity of 50 people shows up, and four buses have to show up before that person who got scanned in 35 minutes ago exits, we assume if they're at the gate, they're going to get on the first available bus to them. So we can go try that, but it's not exact.
Other questions?
Could you walk us through the algorithm that you use to designate probabilities on which train?
So it's like just a proportion, depending on the number of people in each station, in each possible entry station. It's like just a proportion, divide the number of people that are exiting, depending on the stuff. So far, with the data we have, there's really no way to do something more subtle.
On the way in, they all have the same probability of where they can exit, and then on the way out, you would kind of look back. So it's like prior and posterior.
Great. Any other questions?
Is this data available publicly? You have to go request.
I don't believe it's available publicly. It was actually given to a weekend student here, and they weren't able to do as much with it because they just worked on it for 4 hours on a weekend hackathon.
Did a lot with
and
it in
then
4
they-
hours.
And then they passed it on to us. And
Actually,
so
it's
not.
available. If you go
It is available.
Yeah, if you Google pop data channel, there's a tab called data, and you have all kinds of data sets that were collected.
Oh, okay.
But
Right.
the discrete data set that we gave to
Yeah.
It's just a single data set, right? It's
yeah,
not
data set, yeah.
perpetually updated. Yeah, I was going to mention also, it's I think it's on GitHub in a couple of places for a couple of the people that worked on it.
Okay, so we basically had a pop data channel with that in February, right?
I don't know.
Oh, you don't remember? It was Robert Brown who came over, and the city of Port Authority. So we got data from Port Authority, RPA, and a few other organizations, all related to pop train. So So if you are interested to look into more, there's more.
Thank you, everybody.
All right, thank you guys.